Good afternoon, everyone. With a 3-minute delay due to a TSE editorial board meeting here and some technical issues, we are about to start the session on program translation and synthesis. My name is Andy Zeitman. I'm from Delft University of Technology. I'll be session chair today. And the first presentation is not yet on the screen, but it will be presented by Jaemin, and the title is Concrat, an automatic C to Rust log API translator for concurrent programs.
Hi everyone, I'm Jaemin from KAIST. Today I'll present our work, Concrat, an automatic C to Rust log API translator for concurrent programs. This is joint work with my advisor, Sogokon. In this presentation, I'll show how the log API of C is different from the log API of Rust, and why it is important to translate the log API, and how we solve this problem. Programmers use logs to prevent data race. And the most widely used log API of C is Pistiner. It provides a log type and functions to acquire and release logs. Typically, shared data is defined as a global variable, and the log protecting the data is also defined as a global variable. And the program acquires and releases the log before and after accessing the data. However, developers can make a mistake while using logs and fails to prevent data race. First, program can acquire a wrong log. In this example, N1 and N2 are data, and M1 protects N1, and M2 protects N2. The program incorrectly acquires M2 when accessing N1 and fails to prevent data race. Also, programs can acquire a log at wrong timing. In this case, the program acquires M after accessing N, which is too late. And this can also lead to data race. On the other hand, the log API of Rust overcomes these limitations. A Rust log can be considered as a combination of a C log and data. In Rust, programmers create a log with the initial value of the shared data. And since the log and the data are always together, it is impossible to acquire a wrong log when accessing certain data. In addition, Rust introduces a notion of a guard. A guard is a special pointer that can be obtained by acquiring a log, and the shared data can be accessed only by the guard. When the guard is finally deallocated, the log is automatically released. So it means that the guard exists only when the log is held, and the data can be accessed only when the guard exists. Therefore, it is impossible to access data when the log is not held. And this design naturally allows the Rust type checker to detect programmers' mistake that can lead to data race. In this example, the program acquires the log after accessing the data. And since the guard is used before it is initialized, it is a type error in Rust, and the program does not compile. And this makes translating legacy concurrent programs written in C to Rust a promising way to enhance their reliability. Programmers can discover previously unknown data race by translating C code to Rust and type checking it. And noticing this benefit, the system programming community has already started the transition from C to Rust. Linux has added support for Rust in kernel development with its recent release. Unfortunately, manual C to Rust translation is very time-consuming and error-prone. So it would be much better to employ an automatic C to Rust translator, which is much faster and less likely to make a mistake. However, existing C to Rust translators still fall short in translating the log API. The most widely used translator is C to Rust, and its translation is completely syntactic. This is example translation of C to Rust, and it is good at translating the C syntax to Rust syntax, but it does not utilize the log API of Rust at all. First, it simply translates each global variable into a global variable, and it also translates each function call, each C function call to a call to the exactly same function. And the resulting Rust code does not utilize the Rust log API, and this Rust code cannot guarantee the absence of data race. This doesn't satisfy the need of system programmers who want to enhance the reliability of their programs. Then the desirable automatic translation should utilize the log API of Rust. It should combine these two variables into a single one and access the shared data using a proper guard. And we solve this problem by proposing this approach. And we also implemented a tool named Concrat. So in our approach, we first translate C code using C to Rust to Rust code that uses the C's log API. And then we analyze the Rust code to figure out how logs are used in the program. And finally, we replace these C logs with Rust logs according to the analysis result. So this is an example transformation of Concrat. Suppose that our analyzer can successfully find that M protects N. And using this fact, Concrat transforms each line of this Rust code. First, it combines these two variables into a single one because the analyzer informs that M protects N. And then, for each function that uses a guard or data, it adds a variable to store a guard. The name of the variable mguard is determined by the name of the log variable m. Then each function, each statement calling pthread mutex log is transformed into a statement that assigns a guard to the guard variable. And each statement accessing the data is transformed into a statement using a guard. Here, we again use this fact that M protects N to determine this guard name, mguard, from the data variable name, N. Finally, statement calling pthread mutex unlock is transformed into the allocation of a proper guard. And therefore, the goal of the static analyzer is to figure out which log protects which data. And for this purpose, we designed an efficient static analysis algorithm. Details are in the paper. And our evaluation shows that Concrat is applicable to a variety of real-world C programs. Among the 46 collected C programs, Concrat was able to translate 29 programs to compilable C code, compilable Rust code. And 5 programs were compilable only after a few lines of manual fix. So one case of those requires manual fix is an interesting example because it actually reveals a bug in the original C program. The original program releases the same log twice by mistake. And if we translate this code with Concrat, then the resulting Rust code deallocates the same guard twice, which is a type error in Rust. And by removing the second release, we could make this program compilable after translation. And this example supports the common belief that C trust translation can discover unknown bugs in C programs. In conclusion, we propose to replace C logs in the Rust code produced by C trust with proper Rust logs according to the static analysis result. Thank you for listening, and I'll be happy to any questions. Thank you.
Yeah, thank you for the very interesting talk.
Thank you.
In the abstract interpretation community, there's also this analysis of which global variables are protected by which logs. Have you had a look into this, and do you plan on extending Concrat for like using a similar analysis to, I don't know, use this newer locking API?
So that's a very great question, and if you don't mind, can I use my backup slide? So we first considered using. Thank you. So we first considered using abstract interpretation-based static analyzer, which already exists, but actually that was inefficient by being too precise. So our key idea behind our analysis is that the analysis doesn't need to that precise because the Rust type checker is not that precise already. So for example, Rust type checker is not context sensitive or path sensitive. So some complex patterns in C program cannot be simply represented in Rust code. So even if we can figure out that M protects N by path sensitive analysis, it doesn't help because the resulting Rust code simply does not compile because of type error. Rust compiler doesn't perform path-sensitive analysis during type checking. So our idea is that we need path-insensitive and context-insensitive, but very efficient analysis. So we designed the data flow analysis, which is quite similar to those in compilers, and that works much better in terms of performance. So we designed the new data flow analysis. Thank you for the question.
Yeah, thanks for the answer. Great.
Maybe one more question before we move on to the next talk.
Can you explain the overhead of static analysis?
Yeah, thanks for the question. So I have a slide, I guess. So because it is a simple data flow analysis similar to those of compilers, it's very efficient. So we can analyze about 60,000 lines of Rust code in 10 seconds. But so Goblin is an abstract interpretation-based analyzer, and it would be much precise, but it is less scalable, and it requires much more time, maybe 1,000 seconds or more. So it is the overhead.
Thank you.
Thank you.
All right, so let's thank the speaker again.
Thank you.
Okay, great. So hey everyone, great to be here with you all today. I'm Dor. I'm a PhD student at Aviv University in Israel. My advisor, he's in the crowd here, Professor Shahar Maoz. And I will present a technical talk now about introduction of triggers to reactive synthesis. So reactive synthesizers provide correct by construction software development. This means that instead of testing the correctness of a program against a desired specification, as done in traditional software development, reactive synthesizers automatically synthesize a correct program which satisfies the specification. The basic way to write specification is in temporal logic. However, unfortunately, developing specifications in pure logic, such as LTL, is not a trivial task at all. Therefore, researchers have developed three specification languages over temporal logic with advanced elements, such as patterns, counters, defines, and more, that allow to express temporal properties at a higher level of abstraction. In this paper, we first contribute a new novel way to add triggers in specifications for reactive synthesis. We will just explain about triggers in a minute. Then we also evaluated the usability of triggers in practice and conducted a user study with real participants that developed specifications while using triggers. So let's start by defining the semantics of trigger. The full formal semantics of triggers appears in the paper, and here we will just provide a general intuition for it. So as you can see, triggers contain two regular expressions whose characters are Boolean expressions. So when we specify a trigger, we say that whenever the left side regular expression 1 holds, then the right side regular expression 2, should immediately hold afterwards. For example, let's look at this trigger right here. So we say that whenever a robot is loaded and called, it should move or charge for 0 or more states until it is not loaded again. In our semantics, we ignore occurrences of regular expression 1 until regular expression 2 has been satisfied, and then we go all over again. Triggers are expressive and succinct. By expressive, we mean that triggers enable expression of properties that are not expressible in simple LTL. For example, consider the property right here. Proposition A holds at least in every second step, meaning on all even states. So it is impossible to express this property using pure LTL without the introduction of auxiliary variables. With triggers, it is possible, as you can see right here. So trig 2 leads to A. That's the way to express it using our triggers. By succinct, we mean that triggers are also can succinctly express properties that are really difficult to express using LTL. So let's consider the following property. There is no subsequence of the run in which A holds K times, but B doesn't hold. So one would need K-nested instances of the until U operator in order to express it using LTL. However, using triggers, such a statement could be expressed more succinctly, regardless of the value of K, as you can see here. So now, after we better understand the semantics and importance of triggers, let's discuss how to encode them. As both irregular expressions and triggers are not directly expressible in temporal logic, to integrate them into the synthesis problem, we have to find an encoding that preserves their semantics. We chose to do it using finite automata. The first step would be to encode the regular expression in the trigger. So a naive approach would be to encode the regular expression into ordinary finite automata. However, this wouldn't be very efficient, as the size of the automata would be linear in the number of assertions valuation. Instead, we encode triggers using symbolic finite automata. We transform each assertion, maybe I can, never mind. We transform each assertion, assert, in the regular expression into a symbolic finite automata consisting of two states and a single transition between them. An initial state with a single transition labeled by the assertion, as you can see, leading to an accepting state. Then we concatenate all the assert automata into one automaton and perform minimization over it. This method creates a symbolic automaton with size that is linear in the number of assertions and not the number of assertion valuations, which is more compact. Then we have two symbolic finite automata, and we would like to create one symbolic automaton that represents the full trigger semantics. So the construction of this one full automaton is done as follows. Given two deterministic symbolic finite automata, A1 and A2, we construct a new automaton by concatenating them as follows. So we say that whenever A1 accepts, we go to the initial states of A2, and whenever A2 accepts, we go to the initial states of A1. A path pi satisfies the trigger if and only if its computation either traverses between A1 and A2 infinitely often, or from some point on, the path never leaves A1. In the example, here we see that the single accepting state Q1 of A matches our intuition. So we get that either the robot is never loaded and called, or it must move or charge until it is unloaded. Finally, when we have one symbolic finite automaton that represents the trigger, we would like to update the synthesis problem by including this automaton. The update is done by encoding the automaton in the specification language, which is in our case spectra. So we define auxiliary variables whose values represent the states. Then we define safety guarantees that represent the transition of the automaton. And finally, we also define a globally finally guarantees to represent the accepting states of the automaton, as you can see right here. In the paper, we also prove that our encoding is optimal. So in addition to the technical contribution I just presented now, it was also important for us to learn more about the usability of triggers in practice. And therefore, we conducted a user study. The user study was done in Spectra. An advanced reactive synthesizer which we developed in our research group at Tel Aviv University over the past 5 years. We conducted one semester-long workshop in our university with 20 senior final year undergraduate participants. In the workshop, participants completed 4 different tasks by developing specifications in Spectra. It is important to mention in this opportunity that in order to make the evaluation reliable and fair, triggers were presented to participants just as any other language feature included in Spectra. And we haven't asked participants to use triggers specifically or any other language feature. So from the specifications written during the workshop, we collected in total 30 specifications that use triggers. And we identified 285 unique instances of triggers in these specifications. In addition, our Slack communication with participants during the workshop class we had included 103 meaningful commit messages, meaningful mentions of triggers with diverse feedback. So the first thing we did was to evaluate the computation cost of triggers. We analyzed the 285 triggers and found out that on average, each trigger added 2.5 auxiliary variables to the synthesis problem with a median of 2 and standard deviation of 1.2. And that none of them added more than 5 Boolean auxiliary variables. Spectra, our framework, can handle specifications with between 30 to 50 variables pretty easily. So having triggers in the specifications does not come for free, as you can see, but its cost is reasonable in our standards. Since our encoding is optimal, any other attempt to encode or to express the same properties would have at least the same cost. The data we collected also contains many real usage examples of triggers, and they demonstrate the usability of triggers in practice. Here you can see a few selected real usage examples of triggers, but of course there are more. The Slack comments by participants were also positive in general and indicated the triggers were intuitive and easy to use. However, we also observed some drawbacks of using triggers in our evaluation. For example, we found some cases an overuse of triggers where a property could be expressed in a simpler way that doesn't involve triggers at all. So let's consider the following property. The robot should rotate if and only if it is in the orange zone. So we actually see that some participants expressed it using triggers. However, a way more succinct, easier, intuitive way to express it exists, which is guarantee always rotate if and only if at orange zone. So we see that sometimes triggers are overkill, which is kind of interesting. The full findings appear in the paper. Finally, we also introduced 12 examples of idiomatic triggers that are a helpful starting point for using triggers in practice. So, for example, in order to express regular expression should never hold, we can use the first that we see here. And in order to express regular expression should hold in intervals of k-states, we can use the second. And the third is for once regular expression 1 hold, regular expression 2 should never hold. So we hope that using them will increase the usability in practice by real participants, by real users of the triggers. So at this opportunity, we also invite you to check more of our research paper appearing at ICSE. So 2 papers were presented by Shahar and by me in earlier session today. Now we presented one, and I will just move on after your questions to the last one. So thank you so much for listening, and I'm happy to take questions now.
Any questions? So maybe I have a question on the user study.
Sure.
You showed some quotes, and people found it relatively easy and intuitive to use.
Right. Mm-hmm.
But what is the learning curve? I mean, you said that you trained these 20 undergraduates.
Mm-hmm.
What is the learning curve? How difficult is it to learn to get to a stage where people say, this is intuitive?
Oh, well, so that's actually an interesting question that I think maybe the next talk will answer in some way. because the next talk described the workshop class we conducted in general. So yes, basically there is a learning curve while learning how to use Spectra and how to use the features. But what we did was to have 4 introductory classes at the beginning of the semester, in which Shahar and for some of them I taught the participants how to use Spectra. And then we gave them like 1 introductory task and then 4 tasks. And of course we saw some different, we saw a learning curve there, but we collected data globally. And I have to admit that we got this generally happy feedback for all of them.
If I understand correctly, the triggers are kind of a precondition to a sequence of that it should happen before the right side happens.
Right.
And more generally, it's coming from a different field, but the idea of context-aware specifications might be interesting here as well. So you might have specification. You might want to say that something must happen during a specific context. So once there's not only the question of when to start the specific sequence, but also if I want to stop it in the middle, for example, if the context is, if you're out of context or something like that. So it's just a thought, you know, because it really resembles the field of context-aware specifications and modeling.
Yeah, interesting.
All right. Then,
We'll move to the next one.
great. So we already know the speaker. And the next paper is using reactive synthesis and end-to-end exploratory case study.
Right. So hi again, in case somebody joined during the question session. I'm Dor, I'm a PhD student at Aviv University. My advisor is Professor Shahar Maoz. And today I will present now an exploratory case study about using reactive synthesizers in practice. So, as I said just before, reactive synthesizers provide a correct by construction software development, and this means that instead of testing the correctness of a program against a desired specification, as done in traditional programming, reactive synthesizers automatically synthesize a correct program that satisfies the specification. While reactive synthesis enjoyed vast academic interest over the past few decades with many algorithmic advancements and some implementations of reactive synthesizers, its usage outside of academia is still very limited. We wanted to better understand the reasons for the limited usage of reactive synthesis in practice. And to do so, we conducted an exploratory case study to learn more about the challenges users face while using reactive synthesis. For example, we wanted to learn more about the differences between traditional software development and specification development, and about the main obstacles for the wide adoption of reactive synthesis. While we know that answers to some of these questions may be known, there is a lack of evidence about them. And we wanted to find evidence-based answers to these questions. To do so, we used Spectra. Spectra is a reactive synthesizer developed in our research group at Tel Aviv University over the past 5 years, the one I just mentioned before. It is a reactive synthesizer with advanced language features and analysis tools, for example, unrealizability and non-well separation detection and localization tools. Spectra is also unique in the field of reactive synthesis due to the fact it allows users to execute their synthesized controllers, which is a significant step toward using reactive synthesis in practice. For example, right here you can see a running example of a controller I encoded using Spectra of 2 delivery robots. They use an elevator to move between different floors in a building. Notice that only one robot should use the elevator at a time, and that the robot can complete multiple tasks, such as turning on and off lamps. The main setting of our study was a workshop class we had at Tel Aviv University. The workshop included 20 senior final year undergraduate participants in a semester-long project class, and during the semester we gave participants 4 different development tasks they required to complete while developing specifications in Spectra. We explored the process end-to-end, not focusing on a small single step in the process, but instead we looked at the entire process, from the formalization of requirements into a specification, all the way to validation and execution of the synthesized controller. During the semester-long workshop, we collected data using two media. The first medium is Slack. We set up private Slack channels with each team and collected in total over 2,800 Slack messages and 20 supporting documents which they sent for us on Slack. The second medium we used is GitHub. We instructed participants to frequently commit their work into private GitHub repositories we created for them, and in total, we collected over 88 specifications with nearly 600 meaningful commit messages. After we collected all the data during the semester, we employed grounded theory analysis to extract findings from what we collected. In the grounded theory analysis, we systematically open-coded all the Slack communication, documents, and commit messages collected during the workshop. We conducted multiple sessions of such open coding until we organized the findings under teams that I will present to you next. At this opportunity, it is also essential to mention that we strictly follow the ACM 6 of empirical standards for empirical software engineering research for better replicability and transparency of our process and results. In our grounded theory analysis, we've identified 3 different themes. The first is about inherent issues in reactive synthesis. The second is about supporting features and tools. And the third is about issues in specification language and modeling. We will now provide brief examples for each of these themes. The complete findings and explanation about them appears in the paper, of course. So, as part of inherent issues, we found that reactive synthesis required a shift of mindset. For example, as participant mentions, when developing reactive synthesis specification, what should be very accurate in what she doesn't want will happen. And therefore, it requires a shift of mindset compared to traditional reactive, traditional software development. So, as we can see here, as she says, concentrating on what we want to achieve is not enough. Moreover, sometimes we do not even need to specify what we want to achieve, but we must be very accurate in describing what we do not want to happen. This forces a new way of thinking, a more complex one, kind of out of the box. Another inherent issue we found is the gap of knowledge between the developer and the synthesizer. For example, we observed that due to this gap of knowledge, it was hard for participants to understand the expected influence of a small change they made in the specification. As you can see right here, many times we've made a simple change of the spec, and the running times became too large suddenly. And then they actually ask us for a bridge on this gap of knowledge. If it's possible to evaluate the complexity of each construct and add an estimated computation time, it may help a lot during the process of writing a spec. So we see participants actually require and ask us to such a bridging. Under supporting features and tools, we found, not surprisingly, that existing synthesis and analysis techniques don't scale well. These scaling issues are expressed in 2 independent forms. The first scaling issue is in running times, leading to sometimes to very high running times, as you can see here, at least half an hour. And the second scaling issue is about output size and readability. So, for example, unrealizable cores may be really helpful when they include 3 or 4 statements. But it's nearly useless when, like in this example here, they include 14 statements. Regarding specification and language modeling, we found that it was often hard for participants to distinguish between the role of the system, which represents the controller, and the role of the environment, which represents the assumption under which the controller should work. In addition, we observed that sometimes it was quite challenging for participants to use advanced language constructs, such as patterns, mainly because it was hard for participants to fully understand the exact semantics of these advanced language constructs. This point, interestingly, refers to our earlier finding about the gap of knowledge between the user and the synthesizer. Finally, we identified opportunities and action items toward making reactive synthesis more usable. The action items are organized under language and specification quality, tools for analysis and execution, process and methodologies, and performance. The proposed action items are based on our grounded theory analysis, of course, and in the next slide, we will discuss only some of these action items, and you can find them all in the paper. Regarding language and specification quality, we discussed the need for empirical studies on comprehension of specifications and the need for anti-patterns or smells for reactive synthesis specifications. We already presented some initial work on this direction in our New Ideas talk earlier today. Under process and methodologies, we discussed the need for development of methodologies for reactive synthesis specifications that are inspired by existing software development methodologies. We already started to work on this direction in our lab at Tel Aviv. Another promising direction in that context would be on systematic specification review, which is similar to code review. Under performance, we see that despite the many algorithmic advancements over the past few years, considerable running times are still a significant bottleneck in reactive synthesis. Better understanding of activities involved in reactive synthesis development and well-defined methodologies may help in development of heuristics. For example, if we know that certain activities are frequent while developing reactive specifications for reactive synthesis, and the specifications are developed in a certain way or order, we may design heuristics that take it into account and hopefully improve synthesis and analysis running times. Our observation that using advanced language constructs when they are not really needed may increase running times is also suggests the need for automatic detection of such cases in order to make running times of synthesis and analysis faster. So again, at this opportunity, we invite you all to check other papers by our research group. And thank you so much for listening. Me and Shahar are here for the entire conference and happy to answer your questions now or outside afterwards. Thank you so much.
Questions, please.
Permission to ask a very dumb question. This is not my room normally, but how is this different than a programming language?
So,
like a well-specified, like formally specified programming language. Because you're talking about readability and code review and understandability and compilation times and run times. And
yeah, right. So, as I said, there are many similarities between traditional software development to reactive synthesis development. Afterwards, you just write an Eclipse, and code something. But the whole ecosystem is different because here you write logical statements, pure logical statements, and the debugging, for example, is really different because here you don't have like a traditional debugger you have in imperative programming languages, but instead you encounter other problems. For example, unrealizability. Sometimes you may have contradictions in your specification, and debugging such problems we found out that debugging such problems is pretty different than debugging of traditional software. And therefore, it required us and other researchers to develop other analysis tools or techniques. And that's basically create a difference between traditional software development and the specification development. And also the fact you synthesize a controller which you don't really know the details of the implementation, right? Afterwards, you have a controller, which is a code that runs, but here you just specify in general what should happen and not go into like the deep details of the implementation. The synthesizer does it for you. So these are the main differences.
I have a small methodological question. I'm a little confused that I believe that reactive synthesis is a quite difficult problem, and I'm a little confused that you classify tool scalability under tooling issues, not inherent issues. So maybe I don't understand how you have designed your groups in the grounded theory.
Yeah, so of course one could argue and say, tools are under inherent issues. Yeah, but that's the way I guess we found to be more convenient or made sense for us to develop the different teams. But of course, yes, as I just mentioned, the different tools are also, that's an inherent issue in the whole field because the different tools require different mindset, different kind of usage. So yes, so basically it could fit.
So maybe a final question from me, which is not related to the underlying technology, but more to the study that you did. The pieces of text, the feedback we got was extremely verbose, if you ask me, if I compare with other empirical studies. So how did you convince the participants to be so?
Oh, so so we just discussed it in the break on the difference between industrial and academic studies. So here we had students. The students got grades for the work, and they worked really hard to make us happy. So we basically asked them to give feedback and to be interactive and to be responsive. And
Was it graded then?
yes, it was graded, and participants got like 5 bonus points for in order to agree to participate in the study. It was approved by the IRB committee of the university, of course. Yes, but some chose not to participate in the study, but took the class, regardless.
Individual statements in Slack were not graded. There was just one grade at the end of the semester.
Sure, yeah.
We told them that the final grade does not depend only on the final outcome, like is your controller correct, but also that we want to see that you used, that you actually invested in making it during the semester.
All right, thanks.
Thank you.
Thank the speaker again.
So hello everyone, I'm Yong Kiam. So this work was done a few years ago when all of us were based at Carnegie Mellon. Okay. So our lab at Carnegie Mellon, we were interested in looking into systems that look something like the photos over here. So either some kind of plane autopilot or train control, or maybe some kind of autonomous vehicle. Okay, generally speaking, we would call these systems cyber-physical systems. And by that, I mean systems that have some kind of discrete embedded code making discrete control decisions. And these decisions are going to interact with the real-world physics of those systems. So typically modeled using some continuous dynamics, such as ordinary differential equations. So we call mathematical models that combine discrete and continuous dynamics hybrid systems. Okay, so our lab is specifically interested in carrying out formal verification of hybrid dynamics. And formal verification, for anyone who's not familiar, is the use of mathematics-based tools and techniques to obtain rigorous guarantees about those models. Okay. And the reason for doing this, I think, is because if you look at these systems, they are going to be operating in situations which are safety or mission critical. It's absolutely important that we have rigorous and extensive correctness guarantees for the systems. Of course, this is alongside other techniques for validating those systems. Okay. So in terms of verification techniques that are available for hybrid systems, we have some that might be a bit familiar. We have, for example, reachability analysis, and you can see in this picture here, this is a simple model of, say, a bouncing ball. We can think of the ball's bouncing action as some kind of discrete behavior, while its dropping motion is described continuously. So what happens in reachability analysis is we typically get some kind of over-approximation of the trajectory of the system. Well, one of the limitations is that these analyses are typically limited to some kind of bounded space and time analysis. So the other class of techniques that's available for hybrid systems, which we actually use in our lab, is based on theorem proving. And in this case, we can, generally speaking, have more kinds of specifications and more powerful proof techniques. But here, the drawback is that we often have much less automation available. Okay. So one of the main ingredients of this work is this thing called a continuous invariant. And I'll explain what this is in a few more slides, but at a high level, it's a set of states that allow us to, that cannot be left by the continuous dynamics. So once you reach an invariant, you're going to be trapped in it. Right? And invariants have been used actually to improve both of the existing techniques for analyzing hybrid systems. In the case of reachability analysis, for example, invariants can help us to extend these finite time properties to infinite time. Basically, you want to show that certain trajectories enter the invariant and stay safely in an invariant forever. And of course, invariants are sort of the key ingredients for us in theorem proving. And they are part of, for example, proving safety properties for continuous systems. And also, they can act as part of larger hybrid system invariants. So what we did in this work is to build what we call Pegasus, a continuous invariant generator. And we have integrated it with Chimera X, which is a hybrid systems theorem prover. Essentially, the goal of this work was to build Pegasus to help us slay the proverbial hybrid systems beast. Okay, so let me go into a bit of background. I think this picture might be a bit familiar to some of us here. So this is a discrete transition system. We have an initial state in green, and we have an unsafe state in red that we want to prove that the system will never reach the unsafe state. And one way of proving this is to find what's called an inductive invariant. This is a set of states that is closed under the transition of the discrete system. So you can see such an invariant here. And this helps us to prove the safety property because, well, starting from the initial state within the invariant, there's no way for us to leave the invariant. So moving on to continuous systems, now instead of having these discrete states, we now think of the state space as this Euclidean space. So we can still talk about sets of states such as the green initial and the red unsafe state. And again, we can try to prove that continuous trajectories from, say, the initial state do not enter the unsafe states. But we can basically use very similar, by the way, apologies for the syntax. I think they converted my slides, so there's some problem with the syntax. But anyway, so there's a way of, so the idea of using invariants sort of carries over the continuous system. So we essentially want to find a set of states that's closed under the continuous dynamics. Okay, and I think at this point, you might think that actually checking that something is an invariant might seem like a more difficult problem. So it is slightly more difficult, but it turns out that it has been proved about more than 10 years ago that this problem of once you're given a candidate invariant and checking whether it's an invariant is actually decidable. In fact, we have also presented a way of logically describing this procedure so we can actually carry out proofs or, in fact, even disproofs of invariance within logical calculus. Okay. So moving on to what we actually built in this work. So we built Pegasus, a sound automated continuous invariant generator. So this is the high-level architecture picture for Pegasus. Essentially what happens is, while you're carrying out hybrid systems theorem proving, you will break down your hybrid system model into sub-goals, and you will eventually reach some goals about the continuous dynamics. Okay, and now you can send this problem off to Pegasus, and Pegasus will initially start by classifying the problem into maybe it's a non-linear or linear problem, what's the dimension, and so on. And then you will apply invariant generation primitives and strategies. I'll explain what those are in the next few slides. Okay, and hopefully you'll now come up with a candidate invariant, which you would then feed back to Chimera X. And Chimera X will now, formally prove that this thing is an invariant or reject it because maybe it wasn't correctly generated. Okay. So I just want to quickly run through some of the primitives and strategies that's available that we have implemented in Pegasus. So by primitives, we mean sort of standalone techniques for generating an invariant for a given continuous problem. So I guess one of the simplest such techniques is to simply look at the problem and apply some heuristics to it. For example, we can look for terms or formulas that appear in the problem, and we can analyze these using sort of our invariant checker. Maybe if some of them are already suitable invariants, we can use those straight away. But if we want to do something a bit more principled, we can also look for things like conserved quantities of the continuous system. Think about energy, for example, as a conserved quantity. So more formally, we also call these first integrals. And polynomial first integrals, they can actually be generated automatically using linear algebraic techniques. So if they exist, they can be found using such techniques. So we can go beyond first integrals, so we can look for things called second integrals, or also called double polynomials. And for these, linear algebra techniques actually are not enough. We have actually implemented techniques that come from the computer algebra community. And you can even go further beyond the two that I just mentioned. So you can even find so-called rational function first integrals. And these are first integrals formed from the ratio of two polynomials. And for this, we kind of have to combine some of the techniques that I talked about in the previous slides. By the way, I should mention that some of the primes are actually not correct on the slide. So yeah, I think if you access the slides on my page later, you can find the correct ones. So going beyond the more algebraic techniques, within Pegasus, we can also apply more numerical-based techniques, such as this one called barrier certificates, again proposed about 20 years ago. And the idea is basically to find a polynomial which serves as a barrier function between trajectories of, say, starting from the initial state, separating them from the unsafe states. And these polynomials, they can be found using a variety of techniques. Over the last, I would say about 10 years, different groups have come up with different ways of ensuring these properties based on some kind of so-called differential inequality. And the numerical techniques generally are based on sum of squares or linear programming. Okay, so that's all for the primitives that I want to talk about. Now, what we call strategies is ways of putting together different primitives, right? So one of the strategies that we have implemented within Pegasus, which we have found to be very useful, is this one called differential saturation. And what it does is essentially it runs through the primitives one by one, maybe in a loop, to iteratively generate a stronger and stronger invariant until we prove the given safety problem. So, for example, if the shaded blue area is of the state space we are considering, then we can apply, for example, invariant generation based on W polynomials to cut the space in half, and then maybe another technique to cut the space further in half, and then finally we can apply the numerical technique based on barrier certificates to eventually find an invariant that would solve the problem. Okay. So of course Pegasus is a general framework that allows us to put together different primitives. So we can also implement alternative strategies such as this one, which we call the differential divide and conquer. And here, instead of refining invariants, what we're doing is using an invariant generation technique to help us split the state space. So, for example, here in the right three pictures, I've split the state space into p less than 0, p equals 0, and p greater than 0. And then we can divide the problem into these three subproblems and conquer them using sort of recursive techniques, recursively applying the strategy. So in the paper, actually in the journal version, we have a benchmark suite of about 150 continuous verification problems. So I just have about 16 on this slide. And just to show some of the properties. So what we can see actually is that what we found was that actually different classes of benchmarks can typically only be solved using different invariant generation primitives. Okay, and what was interesting actually is that by putting these together inside Pegasus into a strategy, we can actually carry out invariant generation effectively. And in fact, if you look carefully enough, so the DS in this particular column, it's possible that using DS we can solve a problem that no standalone primitive can solve alone. Okay, so in the paper, there are more extensive experiments and results. We solve about 2/3 of the benchmarks that we have collected, and basically we showed that having this framework that allows us to put together primitives and strategies is a good idea. And we're able to also test different configuration parameters in the paper. Right, so to summarize, we've built Pegasus, which is an effective and sound continuous invariant generation framework and it's used in hybrid systems verification. So I'm happy to take questions. Thank you.
Any questions?
Yeah. Okay. So I'm not particularly in this domain, but I have some naive question. So in this system, you are solving, let's say, hundreds of the ODEs together. First of all, what is the scale of the problem you can scale up to? The second thing is, okay, we are, from my understanding, you're trying to model, maybe in the real scenario, you model the real world problem using a bunch of polynomial, partial differential equations, the ODEs. But what comes, the noise part, all the things you cannot model, is that going to eat up your stability region, all these kind of things, invariant region? So, yeah.
Right, it's a great question. So let me answer the first one. So for the fully automated generation, we can go up to, I think, 16 dimensions. We have a few benchmarks at 16. Of course, that depends on whether the differential equations are actually linear or non-linear. For linear, we have much more scalable techniques compared to non-linear. So in our benchmark suite, I would say mostly 2 to 3 dimensional, but we also have going up all the way up to 16. So for the second question, which is, so for this work, it's purely about generation for ordinary differential equations. So if you want to go for things like with noise, you can think about stochastic differential equations with noise, which we have not really tackled, but I believe you'd still be able to find, use similar techniques to generate invariants for those as well. So that's another possibility. In terms of stability, actually, we have other work that looks into, well, not really, we have other works that look into how we can actually formally prove stability for continuous and hybrid systems, but not in this work. Yeah. But generally speaking, if you add more noise, then it's true that the invariant region will shrink, so it might also be harder to find invariants. Thank you.
Many thanks. And we move on to the next.
Hi everyone, my name is Caitlin. I'm a high school senior from the US, and today I'm presenting on ML-based program translation, Perils and Promises on behalf of my co-authors, Aniket, Professor Baishaki Ray, and Dr. Saika Chakraborty. First, why is ML-based program translation important? Well, there exists a large corpus of legacy code written in older languages, such as COBOL and C, that should be translated into modern languages to avoid problems with cybersecurity. However, current models don't work as expected, especially between modern programming languages. You can take a look at the screenshots to the right. That doesn't really look like code that would compile. Our main focus in the paper is the Facebook AI transcoder. It's a model developed by Facebook AI that translates between the languages of Python, Java, and C++, but we mainly focus on Python to Java and Java to Python translation. We are able to make, we're able to take an empirical study on Python to Java and Java to Python translation by taking a sample set of 50 pieces of code in Python and 50 files in Java, translating it into the other one from around 700 of each from Geeks for Geeks. So the format of the code was, there's a main method that has test cases and a method that we want to translate. We treat the transcoder as a method translator, i.e. it translates one function at a time. In Python to Java, the translation issues mainly fell into unexpected additional restrictions and problems with complex structures. In Java to Python, the translation issues fell into mainly problems with complex structures. We're going to take a look at some of the examples of these problems with complex structures now. In Java to Python, one of our main issues was loop conversion. Let's start from the top left. Of the screenshot. On the screen, it initiates a for loop. It says int I is equal to 0, j is equal to length minus 1, and it takes the condition I is less than j. Then inside the for loop, it increments I and decrements j. However, the issue with this is it doesn't translate. It's absolutely fine to write a for loop this way, although it's not very common. This is what we would call a more complex for loop, and it's actually used quite commonly at higher level programming. The issue is it doesn't translate, so we have to find a way to fix it. Now we look at the bottom left. The bottom left is what we transformed this, what we took this for loop and turned it into. We turned it into a while loop. As you can see, the I and j remains the same, and the while loop just takes the condition I is less than j. Then inside the while loop itself, I is incremented and j is decremented. Semantically equal, syntactically works the same. And this ends up translating and gives us a code that runs well. The next issue that we have from both Java to Python and Python to Java translation is type sensitivity. In Java to Python, an array can't be used as a parameter, so we turn the array into a list. We can take a look at the screenshot at hand. It defines a parameter int a square brackets, indicating an integer array. However, this doesn't translate, but when we turn into an array list of integers a instead, it ends up giving us a working translation in Python. In Python to Java, a 2D array cannot be used as a parameter for the same reason as above. It's just going to collapse and not give us something that translates or runs. So this gives us some type of intuition. We all know the large model of ChatGPT, which is a very good model trained on very good data. But even for models such as ChatGPT, we need to know how to ask a question to it correctly. It's not always going to give us the answer we look for. even if we ask it like tons of questions. So this raises a question, how to ask a question correctly. As you can see, when we give a function, when we give the transcoder a for loop, it doesn't translate it, but when we give it a while loop, it translates it. The model translates certain types of structures better than others, probably due to an imbalance in data distribution, when we can confidently say that the model has probably seen many more while loops or less complex for loops than complex for loops. So we need to make the structure we need to turn the structure into its equivalent structure favored by the model that it knows how to translate. And this intuition gives us the idea for the pipeline that we proposed. This pipeline, we take an input. This input can have any type of structure, and we pass this input into a specific structure identifier. And this specific structure identifier, it flags anything that could potentially fail. For example, a complex for loop. And then we take the code from the input, and then we convert it to an optimal structure. The optimal structure for the transcoder would be the while loop. How do we know what the optimal structure is? Well, we use the knowledge of equivalent structures. For loops and while loops can be considered equivalent, and what the transcoder does well, the transcoder works with the while loop pretty well. Then we take this code, we put in the transcoder, which will translate it because the transcoder works with it well, and then that gives us an accurate translated code in but has a while loop. But then we want to take it and turn it back to a for loop because our input had a for loop. So we're looking for a for loop. Then we transform the optimal structure back to the original structure, and we know what the original structure is from the specific structure identifier. And this gives us the output we're looking for. So what happens in the future? The solutions to all such problems that we mentioned today can be fixed by manual changes. So we want to automate the process for all the fixes as we indicated in the pipeline that we showed on the previous slide. It would combine pre-processing, translation, and post-processing, and would also be scalable. Thank you. Does anyone have any questions?
Yeah, this is very interesting. When you say that you want to transcode the end result, you're using the example of you had preloaded it from for loop to while loop, convert between language, and then you want to go back from while loop to for loop.
Yes.
So a little bit of question of why. Partly because I would hope that the large language models, like you said, they're very good at the stuff that they've seen a bunch of, and I would assume that their output is stuff that they've seen. So aren't you going to get more idiomatic code in the output without futzing with it?
So I think the answer to the question is not really. It's not really clear cut. As in, if I only wanted the code to work, then I wouldn't need to translate it back because the while loop works just as well as the for loop. But if I want it to be specifically a for loop for some reason, for some purpose, maybe to maintain the origin, what it was originally, then it would be useful to transform it back. In the end, this last step isn't going to change what the code does. So I think it just really depends on what the user wants.
Thanks for the interesting ideas. I'm just wondering, how does this idea maybe applied to some language with different program paradigm, like Java versus OCaml, or maybe C to Rust, different kind of languages?
Sure. So we haven't investigated between languages that aren't very similar yet, but we believe that we first need to look at languages that can be translated amongst each other more similarly, that have equivalent structures in them. There will be equivalent structures in a lot of different languages. They're not just going to go. They're just not going to be going by the same name, and then they might be initialized pretty differently. And when we get to that bridge, there are definitely going to be steps that we could take. But for the transcoder AI model itself, the Facebook AI model itself, it focuses mainly on Java, Python, C++, which kind of they all have similarities. Yeah.
Hi, I assume you're using the pre-trained models?
Yes.
Could you have trained models that understood the more complicated loops?
Right, so that was something that we considered when making the pipeline. What we found is that pre-training a model is very costly. It's probably very difficult, and it's better to be able to utilize what it's good at now in case that the new model ends up like foregoing its ability to translate while loops. Instead, like it translates for loops well, but not while loops, and then that could cause a potential issue. So it's better to be able to focus on what we know now and then create a pipeline in the future, try to build upon what is good right now.
Do you know if these models can be incrementally trained?
Sorry.
So can these models be incrementally trained, or are they totally batch?
The Facebook AI model, which is the only one we've like currently investigated pretty thoroughly, said that it was trained like not incrementally. Yeah.
So if you train the model for what it can do right now, aren't you then always running behind? Because the next version of the model might be excellent at translating for loops and while loops. So are you always running behind, or at what point will you get even with the capabilities of the model?
Right, so we're saying that until the next version of the model is released, this is probably the best solution. Of course, like it is good to have like better models in the future, but it's right now it's more efficient to focus on this. And once it becomes more efficient to train a model that could that we know with 100 like more than 90% confidence that could translate complex for loops, it's better to work with what we have like 100% confidence right now. So it's kind of an issue with like how conservative we want to be with the model and the work that we're doing.
Any more questions? If not, let's thank Katherine.
Okay. Hello, everyone. I'm Fang Liu from Beihang University, and yeah. Okay. Okay, I'm very glad to share our paper Unsupervised Syntax and Domain-Aware Model for Unsupervised Program Translation. First, I'll give an introduction. To meet new business needs and environments, one software developed initially by one language might to be migrated to another one. So code migration is a crucial activity during the software development and maintenance. There is also a tremendous need for program translation. However, the parallel resources are also scarce in the program domain compared with the NLP, and it is also costly to manually collect the bilingual program data. So to ease this issue, the unsupervised program translation techniques has been proposed, such as the transcoder, just like the previous report. However, this model still needs to be pre-trained, use the super large amount of code corpus, and which is also very expensive. Besides, this model cannot fit well for the language that are not seen during the pre-training procedure. We argue that facilitating the cross-lingual transferability is an effective way to improve the data utilization and also saving computing resources, so we can benefit the program translation systems. So to enhance the model's cross-lingual transferability, we propose a syntax and domain-aware model for the unsupervised program translation. And let's move on to our approach. Before building the model, we first build a dependency graph based on the AST. Specifically, we first extract all the leaf nodes to form the initial node set as the graph, and then we add edges for the node pairs whose distances is lower than a threshold. And then see the model design part. We use a vanilla transformer encoder as the backbone model, and then to enhance the knowledge transfer ability, we augment the encoder with explicit syntax structure information. Specifically, we use graph attention neural network to encode the structural information of the code snippet. And we first encode the code snippet into embedding vector and then build GAT to compute the structure, the output of each token, and with a dependency-aware mechanism. Then we design a structure-aware self-attention to incorporate the structure syntax into the model. That is, we use the representation produced by the GAT to bias the self-attention. And it is also worth noting that the augmentation only occurs as part of the attention heads and the encoder layers. And for the decoder, we directly use the vanilla transformer decoder to predict each token in the translated programs. And for the model training part, inspired by the unsupervised machine translation training paradigm, we train our model with a three-stage strategy. The first is, at the first stage, we initialize our model with two objectives. The first one is a cross-lingual mask language model task, which masks out some of the token some tokens randomly, and then train the encoder to predict them. And the second one is a denoising autoencoding objective, which first crafts the token sequence with noising functions, and then train the decoder to recover the original code. And at each training step, the training pair is monolingual, and then we alternate between the batches of different languages. At this stage, our model can learn high-quality cross-lingual token representations and can become more robust for the noises. And at the second stage, we continuously train our model with the syntax and domain knowledge augmentation, also with the DAE objective. Since it is hard for the DAE to directly guide the GAT model to learn the syntax structure, to address this issue, we propose auxiliary tasks to supervise the GAT to learn the structural information. Specifically, we directly use the GAT's output to predict the distances between the token pairs and the tree depths of each token. And to further encourage our model to extract the more language invariant features, we also design a domain distinguished task by predicting the source text, the type, and optimize the parameters with adversarial training. And here is the final loss. And the training data is still keep the same with the previous stage. And at the last stage, we fine-tuning our model with back translation. Since previous DAE training primarily teach the models to figure out the synthetic disturbance, and where the copying is the primary task. So to teach the model learn to translate between functions from different languages. So we use the back translation in this stage, and the training corpus is bilingual. And here are the evaluation part. For the training data set, we use the Python and Java data set from CoSearchNet, which is much smaller than the baseline transcoder. And for the test data, we following the transcoder directly use the G4G test set and contains a group of the parallel functions in Python, C++, and Java. And for the evaluation metrics, we use BLUE score, exact match accuracy, and computational accuracy to measure the quality of the translated programs. And here are some implementation details. Now let's see the empirical results. We conduct experiments to answer two research questions. The first one is studies how effective is our model for program translation when compared with the advanced baselines. We choose three baselines in this experiment. The first one is the transcoder, which is the first unsupervised program translation approach that is trained on a huge Python, Java, C++ monolingual corpus. And the second one is transcoder star, which is implemented by retrain the transcoder using our small scale data set. And the third one is CoT5, which is a widely used encoder-decoder model that is pre-trained with CoSearchNet and the BigQuery dataset. As seen from the results, a transcoder can perform best since it is trained on a huge data corpus. And when we change the training data to a smaller one, the performance drops a lot. The poor performance can be attributed to the simple data processing and the training objectives they used, and they didn't consider any syntax constraints or the domain knowledge. And our model can achieve comparable results with transcoder and even outperforms it when on the Python to Java translation, even with smaller training set. And when compared with COT5, our model can outperform it substantially. And this further suggests that the large pre-trained models like COT5 may also not behave well when the data set used for the supervised fine-tuning is not big enough. And for the second research question, we studied how do different components in our model contribute to the performance improvement. We conduct an ablation study by removing the syntax augmentation and the domain-aware pre-training from our model. And can be seen from the results, removing each task can lead to the performance drops, and the effect of the syntax augmentation is big. And for the third research question, we examine how well does our approach perform in unseen language translation. Since in our training set, we don't use the C++ language, and we conduct experiments on the translation between the C++ and Python or Java. And the setting and baselines are also used the same in RQ1. And from results, we can see that since transcoder, it has been pre-trained using the C++ language, so it can achieve the best performance. And for the other three baselines, for the other three models, C++ language is never seen during their pre-training procedure. So among these models, our model can perform best. As C++ and Java are more similar in the syntax and the code morphology, so we can see that the exact match accuracy and the blue score are higher. On the contrary, the syntax and implementations between Python and C++ is vary widely, so the code T5 and the transcoder star performs badly. And we can see that in this scenario, the improvements of our model are more significant. This can imply that augmenting the model with syntax and the domain knowledge can enhance the cross-lingual transferability. So it can also lead to a great performance in unseen language translation. And for the last research question, we studied how useful are our model in practice. Since in previous, we used the BLU4 and the exact match accuracy score to evaluate the quality. And these two metrics may not directly measure the semantic correctness of the results. So in this experiment, we used the computational accuracy to evaluate whether the programs can generate the same outputs as the ground truth when using the same input data. And the results show that our model can achieve comparable computational accuracy scores with transcoder and outperforms other approach by a large margin. And here we present the visualization of the encoder output features. Figure B shows the results of the vanilla transformer encoder. We can see that the data points of the different languages are well separated. This suggests that the vanilla transformer encoder is more sensitive to the language types. And in our augmented encoders, the data points are mixed together. So it suggests that our model is more robust to the language type. So through the domain distinguishing adversarial training and the syntax structure modeling, we can distill more complicated domain invariant features, and thus can enhance the cross-lingual transferability. Finally, I'd like to make a conclusion. In this paper, we built a novel approach for the unsupervised program translation, which leverages the syntax structure and the domain knowledge to enhance the model's cross-lingual transferability, and also present a new unsupervised training paradigm. Despite training with fewer data, our model can achieve comparable results with large pre-trained models, and especially on the unseen language translation. Okay, thank you very much for your kind attention.
Thank you.
Thank you.
And there's already a first question there.
So lots of interesting ideas packed together. Oh. And so did you guys study, because there's many different ideas combined together, did you actually separate which idea contributes more, which idea contributes less? Is it in the paper?
Yeah, we conduct the ablation study here. We found that the syntax augmentation has the bigger effect for the performance improvement. Yeah.
Okay, so yeah, to be sure, that's another question that we can connect offline. So I see that one of the interesting ideas is you are using a transformer together with a graph neural network.
Yeah.
But you understand that in the transformer, the unit is the token. And in the graph neural network, the API, this is a complete API name, consists of multiple tokens. Yeah. So I'm just interested to know the detail, how you map this kind of a node in the graph neural network to the tokens in the transformer.
Okay. Let's get back to the graph building part. Yeah, here is an example. We don't show the subtoken for the simplicity, but before we build in the graph, we first extract all the tokens. That is also the leaf nodes of the AST. And add edges for the token pairs for which distance is lower than a threshold sigma. And for the subtokens, which from the same token, we use the same distance to add edges for between each other. Yeah.
Thank you.
So when you said the size of the training corpus, you just said huge. Yeah. How many lines of code are we talking about?
Do you see the pre-training data size?
Yeah, the training, the size of the training set.
So here.
The 120 million. Okay.
The first table.
Yeah. Okay. That's very useful. The second thing that I wanted to poke at a little bit. This is all unsupervised. And you have also the computational accuracy question. So I assume that there's unit tests around.
Yeah.
Have you poked at, instead of it being unsupervised, like move to sort of semi-supervised, like out of the set of possible translations right here, which one makes the tests pass? Have you gotten that far yet?
Yeah, the data set also contains some the unit test to evaluate the correctness of the program. And during the testing process, we can use the greedy decoding to get only one program, or the beam search can get several, 5 or 10 programs. And in our experiment, the results, we only use the greedy decoding, so we can get one best programs to test the semantic correctness. Okay, thank you.
Any other questions? If not, then we thank the speaker.
Thank you.